Okay, we're going to pick up where we left off. Section 3.7 is doing derivatives of parametric equations. And if you take calculus, you probably won't see parametric equations until Calc 3. So for this section, a lot of you will never even ever see this again. But we are going to just touch on it lightly. I'm only going to spend one day here. It's not difficult. At least the part we're going to do is not difficult. It can get very involved, but we'll save that for the people taking Calc 3. So what is a parametric equation? Well, first of all, it's a pair of equations that work together. So they're parametric equations. They are two separate equations. You have one equation that will define your x, and a separate equation that will define your y. And both are in terms of a third variable. And the most useful application to this is to have your third variable be time. So just as a quick example, say I've got a pendulum swinging in an elliptical pattern. I don't know if you can see that very well or not. If I go upside down. It's going to swing in an elliptical pattern. Okay. Keeps going around and around and around. So if I do that on paper, just keeps repeating itself. Okay, so I'll pretend that that's one big fat line there. What we can do is give a pair of a pair of equations that will give me the x-coordinate and the y-coordinate at a certain time. So for this one, let's say that the x part of each ordered pair is given by 5 cosine t, and the y part of the ordered pair is given by 3 sine t. This will make an ellipse. And again, the coming up with those equations is not something you would have to do. So what I first want you to be able to do is learn how to graph a parametric equation on your calculator. So what you need to do is change your mode to par mode. Stands for parametric. This way. Mode. So off of function mode into par mode. I've already done mine. And now if I'm going to graph that, I go to y equals. You'll see there's a pair of equations there in terms of t. So if I clear that out, I've got 5 cosine. And now when I go to hit my old x button, you see there's an x, t, theta, and n. These are for all the different modes that your calculator might be in. The t is for parametric mode. So when I hit that, I don't get the x this time, I get the t. And then 3 sine t. So it automatically knows by the mode which one of these variables to put in there. Now my window, you've got to plug yourself back to trig. Remember, the period length here is 2 pi. So I want the t to go out to 2 pi, from 0 to 2 pi. And my amplitudes, it's going to go up and down 5, and then out, left and right 3. So, or no, left and right 5, up and down 3. So x is left and right. So the window, to set that up, I want t to go from 0 to 2 pi. T-step, I'll go every quarter pi. It doesn't matter. 1 is fine. Actually, I'll go 0.5. Make it do a lot of points. X is going from up and left and right 5, so -5 to 5. And then my y's are going up and down 3, so -3 to 3. When I hit, let's see, go back to the y equals. I want to make that do that circle thing and run around the graph. Oh, didn't do it. Oh, it went fast, that's why. Let me go back to the window again and make that slow down. Make this go by 0.1 so we can get a little bit better. There it is. Now you can see the circle running around the graph. Slowed it down a little, made it do more calculations. And it just keeps continuing. If I go back to the window and I make it go from 0 to 4 pi, I should see it run around that circle twice. So there's one time around. Here it comes again the second time around. And all because we knew that the period length for sine and cosine is 2 pi to make it complete itself. All right. Oh, we're going to let this one be our first example, by the way. There's going to be a lot in here. So graphing, you got to be in parametric mode, and then set the window up. Okay, now I'd like you to make a table of points, but our table is going to have 3 variables in it. Our t value, x, and y. And for the table, I want you to go from t equals 0 to 2 pi. And let's go every quarter pi, pi over 4. That won't be too many points then. So 0, pi over 4. Just keep adding on a quarter pi. Pi over 2. Adding on a quarter, that's 3/4. Add 3/4 plus 1/4 is 1 pi. Adding on a quarter again, that's 5/4. Then we'll be at 1 1/2. 1 3/4, that's 7 pi over 4. And then my last one, 2 pi. Okay, to get these values, I'll just set my table up to do this. The equations are in there. So if I go to table set, I want the table to start at 0 and go every pi over 4. And again, the calculator won't work with the fractions, but it just turns them into decimals. Now when I go to the table, these are every quarter pi, and these are my x and my y's. So I'll just copy now. So when 0, x is 5, 0, x is 5, y is 0, just copying. 3 1/2, 2.1, just 0, 3, negative 3 1/2, 2.1, negative 5, 0, negative 3.5, negative 2.1, 0, negative 3, 3.5, negative 2.1, and the last point is 3.5, 2.1. Okay. Actually making that sketch now, real quick. X is going out to 5. 2, 3, 4, 5, and then y went up to 3. So when x is 5, y was 0. 3 1/2, 2.1, 0, 3, negative 3 1/2, 2.1, negative 5, 0, negative 1, 2, 3 1/2, negative 2.1, 0, negative 3, 3 1/2, negative 2.1, and then there's our ellipse. All right, so no calculus yet, just graphing and using the calculator, making a table of points. Now to find the derivative, remember our derivatives, we always say y prime, but really what we're finding is dy dx. That's the derivative of y with respect to x. We've been calling that y prime all year. Well, I don't have a single y equation in terms of x. I've got an x equation in terms of t and a y equation in terms of t. So what we can do to get dy dx, I can only do the derivatives with respect to t because that's the equation that I have. So I can find dy dt, the derivative of y with respect to t, and if I divide by dx dt, the derivative of the x equation with respect to t, because I have both of these equations, so I can find both of these derivatives. Because both of these x dx dt would be the derivative of this one, dy dt would be the derivative of this one. Well, if you look at what happens, to divide by a fraction, I flip and multiply. So I'll have dy dt times, if I flip this over, dt over dx, the dt's cancel, and I'm left with dy over dx. So if we have parametric equations, in order to get the derivative, we're going to divide the two parametric equation derivatives. So technically it's going to be y prime over x prime of my two equations in terms of t. That's what's going to get me dy dx. So not so bad. So I will do that's what I want to do next, is find dy dx. So I'll go dy dt, which I'll call y prime. So looking at y, I got the equations at the top of my paper now. I'm going to do the derivative of 3 sine t. So the 3 is a multiplier. The derivative of sine is cosine. So it's going to be 3 cosine t. And then the derivative of the angle is just 1. So just 3 cosine t. And now I need dx dt, which I'll call x prime. That is the derivative of 5 cosine t. So the 5 is the multiplier. So the derivative will be, and then the derivative of cosine is negative sine. So the 5 times a negative sine, and then the derivative of the angle is 1. So it's just negative 5 sine t. So now to get my dy dx, I just have to divide those two derivatives, the y derivative divided by the x derivative. So it's going to be 3 cosine t over negative 5 sine t. I can leave it like this, or simplify, knowing that cosine over sine is cotangent, negative 3/5 cotangent t. And now I can find the derivative value at any t value. So let's say I wanted to find it when t equals, pi over 4. So the last part of this is going to be to find dy dx when t equals pi over 4. So that's just plugging pi over 4 in for the t. So that will equal negative 3/5 times the cotangent of pi over 4. Or I could plug it back into this one too. So to get that value, calculator work, negative 3/5 times cotangent is 1 divided by the tangent, and then pi over 4. Negative 0.6. And if you look at your graph, when t equals pi over 4, I'm talking about this point here. Our derivative value came out negative 0.6. That's giving me the slope of that tangent line. And it seems reasonable because I got that negative slope going there. Okay, let's try one more of these. One that